we are going to find that this is a very important question if you are curious about what happens to subducted lithospheric plates or about the source of hotspot volcanism as we have here in the Pacific Northwest's Columbia River basalt group. So these are important questions because you might be thinking, does the mantle convection occur throughout the mantle, or do some regions convect more efficiently than others? This is a slice through Earth, and for simplicity, we've blocked out the core of the Earth. So this is basically showing the lithosphere at the surface as well as the mantle, so the silicate part of Earth. And we will talk about this figure in detail later, but to orient you a little bit, AF is showing us where Africa is, SA is showing us where South America is, NA is where North America is. So some of our orientation there. And we see that this image, which is a colorful representation of seismic wave speeds, where we have some intriguingly warm areas and some intriguingly cold areas, we also notice that there are these two dashed lines, and that these lines look as if they coincide with a rapid transition from one color to the other. So if we're going to understand what seismic tomography is telling us about the Earth's mantle now and how it may have gotten that way in the past, we want to think first about the significance of those lines. On this summary diagram, we are looking at P wave velocity in kilometers per second and how that increases with depth below the surface. Throughout the lithosphere, we see a really rapid increase in the P wave velocity. And then in the lower lithosphere, that velocity is somewhat static or stable. We see a drop in velocity at the low velocity zone. We've already talked about that. But if we look down at this deeper part of the mantle between 400 and about 660 kilometers depth, we see these three distinct stair steps, okay? Overall, we see a trend of increasing seismic velocity, but those three distinct steps we'd like to understand. And the take-home message today is that we believe that these are due to changes in the density of the rock in those areas, and the density increases dramatically as we have basically a metamorphic change from one mineral phase to a different mineral structure. And I've outlined here the mantle transition zone with these blue dashed lines so that it looks similar to the previous image. All right, well, in order to think about what's going on here, we take a look at the results from high pressure experimental petrology. This is a cross section of a high pressure experimental furnace that can control both the temperature and the pressure during an experiment. Here we see the wires. This is the thermocouple that comes in to control the temperature in the sample. And over here to the right, we see the sample much larger. So we've measured out a powder that is similar to mantle peridotite. We insert it into a little crucible that can heat up, and we have talc around that so that we can increase our pressure and get deformation, but we want a confining pressure. It's important that we introduce a sample whose composition matches olivine-rich peridotite because that's what we think is in the mantle. And we can investigate what minerals will grow and reach stability at the conditions of the mantle transition zone. This diagram summarizes the results of many careful experiments. And I want to point out to you that we have temperature along the x-axis, pressure along the y-axis, and at the top, we're indicating that we're using the composition of a pure forsterite olivine, that magnesium-rich olivine. And when we look at the results, anywhere we have an area bounded by these phase boundaries, it means that within this area, the stable mineral phase is indicated. So olivine has the alpha olivine structure. If we took something that was pure olivine and we kept the pressure the same but heated it dramatically, we could melt that olivine, okay? But we're interested in the solids here. So we see that olivine is really quite happy at about 1500 degrees C, and the pressures, are able to range from about 11 gigapascals up to maybe 15 gigapascals. So remember, what is a gigapascal? Let's think about this in terms of the depth within Earth. And here I've put up a reminder that 1 gigapascal, clear down here at the bottom, is equivalent to about 30 kilometers depth. And so if 1 gigapascal is 30 kilometers depth, then what is the distance in the Earth for 10 gigapascals? I'm gonna let you fill in the blank there. Okay, notice that at higher pressures, there are 3 additional solid minerals that are possible. The mineral wadsleyite, also known as beta form olivine, the mineral spinel or gamma form olivine. This is also now called ringwoodite after a famous experimentalist, Ringwood. And then finally, if we were to take wadsleyite here at roughly 2000 degrees centigrade, and actually this my control panel, yes, 2000 degrees centigrade, and we raise the pressure, we would actually create a situation where perovskite would be the result of that metamorphism. However, perovskite requires only 1 magnesium, 1 silicon, and 3 oxygens, leaving us with extra magnesium and oxygen. And that will form the mineral periclase, magnesium oxide. Okay, so here I'm showing that these are all phases made with the same composition if we add the periclase and the perovskite together. So what is different about all of these minerals? Well, I've added the representation of olivine's crystal structure, ball and stick diagram. Remember, which is going to be the biggest element here? Magnesium, silicon? Hopefully you chose oxygen. These anions are the larger balls in the diagram. And then we're going to have silicon and magnesium taking turns in these other locations. So we see that we have a slightly different structure for wadsleyite and yet a different structure for perovskite. I have not to scale, but deliberately made my olivine image larger than the wadsleyite and the perovskite image. Why do you think I'm maybe showing a large unit cell for olivine and a smaller unit cell for perovskite? Well, if we look at one of the consequences of olivine changing to one of these higher pressure polymorphs, we can compare the density. And we see a really distinct difference. Olivine, 3.2 grams per cubic centimeter. Wadsleyite, significantly more dense, and perovskite, more dense yet. So why should this increase in density matter? What do you think? Well, even though we report our experimental petrology information in a phase diagram with pressure increasing upward, remember that our seismic diagram was talking about depth into the earth. So I like to basically flip the diagram, which makes it rather hard to read, but I've done my best here. So now perovskite is going to be our deepest high pressure polymorph, then wadsleyite, ringwoodite being over here with the spinel form, and olivine near the surface. And if we take it one step further, then we can start to think about how this lines up. And it turns out that there's a very good correlation between where we have the jump in seismic speed at 400 or 410 kilometers depth, the jump in seismic wave speed at about 500 kilometers depth. It's not always there, but sometimes it is. That corresponds with, at a mantle temperature, that corresponds with the stability region for ringwoodite. And that final jump, stair step, at 660 kilometers depth matches very well with where we expect perovskite to begin forming. So what we've done here is we've talked about the mantle transition zone as being first recognized in seismic wave velocity profiles. For example, the S wave might increase by its velocity by as much as 10%. These jumps in seismic wave speed happen primarily at 410 and 660 kilometers depth. Also, there's one at about 500 kilometers that sometimes shows up. We now interpret this increase in speed as being related to the metamorphosis from one mineral phase of olivine in the upper mantle to another more dense, more stable phase. And if we were to take a look at where the pressure matches what we think is a reasonable temperature distribution for increasing depth in the mantle, keep in mind here, we're starting at 10 gigapascals or 300 kilometers depth, and we're starting at about 1600 Kelvin. And we see that we're getting, we're crossing these boundaries from one mineral phase to another at exactly the right depth. And this works best when we use an olivine that is approximately 95% forsterite, and that's some work by Paul Asimov at Caltech, among others. So we go back to this initial slice through Earth where we're looking at both vertical and horizontal changes in seismic wave speed. We're seeing some really intriguing patterns here that we're eventually going to talk about in terms of plate tectonics, topics such as subduction, or perhaps mantle upwellings in a hot plume of material that could create hotspot volcanism. But in the meantime, I'd like to point out to you that the mantle transition zone, which is this dashed area here, is very often looking like a density boundary between areas of mantle that are dramatically different from each other.